This is Amardeep Srivastav, and in the previous lecture, I have completed the concept of imperfections in solid. That is, I have completed the concept of imperfections, that is, defects in solid. Now, in this lecture, I would like to extend my lecture to the point through electrical properties of material. That is, I will classify energy bands in solid. That solid will include conductors, semiconductors, and insulators. I'm using WD Callister and SP Seth for reference. You can also use SP Seth for electrical and magnetic materials, and you can use few topics related to WD Callister, and I will mention it in in the description box. Now, what do you mean by the term energy band? Energy band. In normal excited state, that is when an electron is in normally excited state, the electrons in the atoms occupy a definite amount of energy and having certain energy level. That is, when an electron is in normal state, it will have some energy, and that will have some energy levels. And at that time, the energy level is known as energy bands. What do you mean by the term band gap? I would like, before explaining band gap, I would like to explain two terms related to band gap, that is valence band and conduction band. Band gap will represent the difference between, you can say that band gap is the energy gap between conduction band and valence band is called band gap or energy gap. You can say valence band क्या होगा, जहां पे इलेक्ट्रॉन जाने की कोशिश करेगा. Conduction band will be the band where it will get energy and will jump to valence band. Valence band. Now, I would like to explain or differentiate conductor, semiconductor, and insulator as per their band theory. So, let me draw a chart that is for conductor, for semiconductor, and for insulators. Now, in case of conductors, energy band overlaps. In case of semiconductor, energy band or energy gap, you can say Eg is less. And in case of insulator, Eg, that is energy gap, is very more. So that electron from conduction band will not jump to valence band, so that there would be no conduction. Now you can say that in case of conductor, as energy band or energy gap is overlapping, so you can say that if there will be slight excitation that will cause electron to jump from valence band to conduction band. That is, with slight excitation, electron will jump from valence band to conduction band. Okay. Now, in case of semiconductor, as the Eg is less, that is band gap is small, so it requires some small amount of energy. Either you can provide it in form of thermal, or you can provide it in terms of photon, or equals to h nu. It will require a small amount of energy to pass into the conduction band. That is, the electron which is placed in a valence band will require a small amount of energy to just jump from valence band to conduction band, and hence conduction will possible in case of semiconductor, because Eg is less, that is air gap is less. Sorry, air gap. I am talking about energy gap. Now, you can say that in case of semiconductor, Eg varies from near about 0.12 electron volt to 5.3 electron volt. Now, in case of insulator, as electron do not leave the valence band, even by thermal excitation. Why in case of insulator, if you provide a thermal excitation to that insulator, there will be no electron jumping from valence band to conduction band, because their energy gap, that is Eg, is very high. That is, you can say that it's nearly 6 electron volt. Electron volt is the unit of energy. Now let me show you how this is possible. Now in case of conductor, you can say that there will be overlapping of valence band and conduction band. So this is conduction band, let's say, and this is valence band, and this overlapping I represent it by, you can say this is the overlapping. Eg, that is the band gap or energy gap, will be equals to 0 electron volt. And now in case of semiconductor, energy gap is very less, so you can say that there will be a transmission of electron from valence band to conduction band if we provide little amount of energy, that is nearly equals to 1 electron volt to the electron. Now this is conduction band and this is valence band. If you will, in conduction band and valence band, there are holes, and in conduction band there are electrons. So if we will provide the energy near about 1 electron volt, the electron will start jumping from leaving the valence band and occupying the position of conduction band. Now in case of insulator, you can say that the energy gap is very high, that is nearly equals to Eg nearly equals to 6 electron volt, which is very high. So there will be no conduction in case of insulator. Solid atoms very close to each other. Let me discuss you some point. In case of solid, atoms are very close to each other. Electrons experience attractive force from other nucleus also. So you can say that in case of solid, if you will talk about the electronic configuration or electronic force of attraction or repulsion, you can say that in case of solid, atoms are very close to each other. That is, atoms very close to each other. Electrons experiencing attractive force from other nucleus also. That is, the electrons are in periphery of other nucleus also, so they are experiencing some of the attracting force. So that energy will vary, and that variation energy will cause energy band. Now fully filled band, electron do not participate in conduction. If the energy band is fully filled, then there is no need of electron to take part in conduction. Now let me show you what is Eg, that is energy band through energy chart. Now this is energy level, that is, let's assume conduction band, and this is valence band. This is conduction band. I am plotting this curve against energy plot. Conduction band, and this is valence band, and this gap, that is the gap of energy required to electron to jump from valence band to conduction band, is Eg, that is the band gap. Now this is known as Ec and this is Ev. What is Ec and Ev? I will explain. Ev is the lowest energy level of conduction band. Lowest, that is, Ec is the lowest energy. Now this electron will jump from valence band to conduction band, and this energy is known as energy gap. Now Ec is known as highest energy level of lowest energy level of conduction band. Ev is known as highest energy level of valence band. Now Eg is energy band gap or forbidden energy gap. Forbidden means why? Because in this region there will be no electron, so it is known as forbidden energy gap, and Eg equals to Ec minus Ev. This relation is important. Now valence electron in conduction band do not participate in conduction, do not accept the applied voltage. That is, if electron will jump from valence band to conduction band, then after the electron reaches to the conduction band, the electron will not participate in conduction, and it will not accept the applied voltage. That is, either you will apply an energy source or to any voltage to that electron. It will not accept any sources to just conduct. Now let's assume, I'm taking sodium atom. It has 11 electron, that is 1s2, 2s2, 2p6, 3s1, 3p0. This is the valence band, and this will known as conduction band. Conduction band. Now, in case of forbidden gap, why there will be no electron? Because to conserve momentum, that is, for the conservation of momentum, that is MBR equals to NH by 2 pi. Electron can only present in band. Why electron can only present in band? UPSC can ask a question, why electron we can only expect electrons in bands. So you can say that to conserve momentum, that is to follow the law of conservation of momentum, that is MVR equals to NH by 2 pi, electron will only present in the bands. Now, in case of metals, the electrons of electron cloud participate in bonding, and also they are free to move, therefore participate in conduction. In case of metals, I have already told you, there are pool of electrons, so they will participate in conduction. Now let me give you a relation. Eg, that is energy gap or energy band gap at temperature T, equals to Eg at temperature 0 Kelvin minus beta T. This is the important relation you have to remember. What do you mean by term Eg of T? That is energy gap at T Kelvin, that is energy gap at T Kelvin, and Eg0, energy gap at 0 Kelvin. Beta is the material constant. Material constant. Now this relation is very much important, you have to remember it. Now I would like to give you some practical data for silicon and for germanium. Silicon and germanium are the heroes of semiconductor, as we already know. At 0 Kelvin, from that relation, Eg0 will be 1.21 electron volt, and at 300 Kelvin, Eg300 will be, that is Eg300 Kelvin will be 1.1 electron volt. For germanium, at 0 Kelvin, Eg0 will be 0.78 electron volt, and at 300 Kelvin it will be 0.7 electron volt. Now let's talk about insulator. Let's know the very much interesting point about insulator, that is when an insulator in molten state, it is a good conductor. Now semiconductor at 0 Kelvin will behave like an insulator, and above room temperature it will act like a conductor. Please kindly remember these points, because you can expect a question related to these points in assertion region question. Example of semiconductor is germanium, silicon, gallium arsenide, we all know. Gallium arsenide जो होता है, it is used in remote LED. Silicon, germanium, you all know very well. Now Eg is equals to Hc by lambda. This is a relation of energy gap or energy, you can say that. Lambda is in micrometer, hence Eg will be in electron volt. Now how an insulator breaks, that is breakdown mechanism of an insulator. So there are three ways, that is it can be a thermal breakdown, It can be an electric breakdown or it can be a chemical breakdown. We don't need to go in very much detail, and if I have to clear it, then I will go in my next few slides. Now start. I'm going to start conductor. Sorry. Ohm's law and electrical conductivity. In case of conductor, we all have read these topic, but I would like to explain it. If you want to go in deep, you can refer videos of analog electronic in my playlist. I have completed in very depth. So let's take a conductor, and I have connected it with a battery. Now I have connected with the battery V or E. You can say that V or E, and I is the current flowing through that conductor, and these are the electrons which are started to move from positive terminal to negative terminal. Now let's take some assumption or some notations, that is N is the free electrons per meter cube, that is electron concentration or charge carrier concentration. I have explained it in very much detail. You can refer my analog basics lecture. Now I am taking as Vd is as drift velocity. Now what do you mean by the term drift velocity? It is the average velocity acquired by the electron under the influence of electric field is drift velocity. That is, electron will observe or electron will face some extra amount of energy when we will connect it with an external battery source. Then that electron will translate from or drift from one position to another due to this battery, and the external drifting is known as drift velocity. Now let me introduce a term, randomness of electron. Randomness is inversely proportional to drift velocity. Please remember this topic, this point, drift velocity. As drifting increases, randomness decreases. So you need to remember this, because they can ask or they have asked question related to this. Now let me introduce a new term, tau, which is known as average collision time. I need not to go in depth with this topic. In case of material science engineering, if I will go through the technical portion, that is for electrical and magnetic material, I will explain you in very much detail, or you can refer my analog electronics lecture. Now the average collision time, tau, will be inversely proportional to root of temperature. This term you have to remember. As temperature will increase, collision will decrease. Kindly remember, engineering services examination, you can expect question related to this. Now now as per Ohm's law, as we know that V is directly proportional to I. For removing proportionality constant, V equals to R into I. But remember, R is not the function of applied voltage and current. Always remember, R is not the, please remember this point, R is not the function of voltage and current. Now as we know that R equals to rho into L by A. If I am taking a conductor of size of like this, having cross sectional area A and its length is L, so you can, and its resistivity is rho, you can say that R equals to rho into L by A. Rho is the resistivity of the material, that is in ohm meter. L is the length of that conductor. A is the cross sectional area of that conductor. Sigma equals to 1 by rho. Sigma is known as conductivity. So as rho equals to rho, unit of rho is ohm meter. So electrical conductivity unit is ohm meter inverse. Per ohm per meter, you can say. What do you mean by the term sigma? Sigma will represent the current carrier capability of that material. That is, the material will carry how much amount, or without any obstruction, how much amount of current it will carry. That is the current carrier capability, current carrying capability of that material. So you should know the fact that resistance is not the function of applied voltage and current. So you can say that V equals to R into I, and using R equals to rho into L by A, L by A into I. Now transferring this I, now you can write it as I by A equals to 1 by rho into V by L through this equation. You can say that, and as we know that current crossing per unit area, that is I by A, you can say that the current density J, that is its unit is ampere per meter square. Now you can say that this is J equals to 1 by rho is sigma, potential per unit length, voltage drop per unit length is electric field E. So you can say that J equals to sigma I. This is the another form of Ohm's law. You need to remember this point anyhow. It's the another form of Ohm's law. Ohm's law, where J is the current density, sigma is the electrical conductivity, E is the electric field density, or J unit of J is ampere per meter square, unit of electric field is volt per meter. Now I would like to pause my lecture here, and I will explain the force experienced by electron due to applied electric field in my next lecture, and I will explain Weinstein-French law in my next lecture. So I would like to say that please kindly join my Telegram app so that I can provide the PDF of my lectures, and also we can have fair discussion about the questions that they ask. You can solve so many doubts, or you can also prepare alongside. So try to be on time, and thank you for watching. Thank you so much.